Hey, this is Mr. Aiden. This is our last video in Unit 7, Diffie-Qs, and we're going to be taking a look at exponential models with Diffie-Qs. So this is kind of the last little bit of application of differential equations that we'll hit in AP Calculus AB. So let's get to it. So how do we do these modeling population with differential equations? Now, you've seen this before in pre-calculus. You've seen this before in Algebra 2. You've seen this before in Algebra 1. But you haven't been able to apply calculus with it. So obviously everything becomes a little bit easier with calculus. So you've seen this before where, let's say the rate of change of a population is going to be proportional to that population, which means if that population doubles, obviously the rate of the babies come in are going to be doubled. They do this a lot with bacteria or mosquitoes or bunnies, or even people. And so what it say is the rate of change of the population, the change of population with respect to time, the rate of change is proportional to the P population. And let's say the time is in days, it could be in years, it could even be in seconds or anything like that. So we have what's called a differential equation here. And so we're going to separate the variables, aren't we? 1 over P dP is equal to K dt. And so we have this. This is very analogous if you take my AP Physics Calculus class. This is very analogous to the when something hits terminal velocity as well. Okay, is very, very similar when we are proportional. That friction is proportional with relationship to the velocity. And so this is primed and ready to integrate. And we're going to set our limits of integration. So we're going to go from our population, from our initial population, to our final population at some point in time. And I can call that P at some point in time. My time obviously is going to go from 0 time to some time t. And so I'm going to do my integral here. What's my integral of 1 over P with respect to P? That's natural log of P. And we're evaluating that from P naught to P at some bit of time. And what's my integration of K with respect to t is kt, and we're going to go from 0 to some time t. And so let's take a look at when we put in these things. So we have natural log of p at some value t minus natural log of p at some initial value at the time, the initial population obviously. And we have kt minus k times 0. Okay, and so if you remember my properties in pre-calculus as well as Algebra 2 with respect to natural logs, when we subtract two natural logs, it is like dividing. So natural log of p at some value t over p naught is equal to kt. And now I'm going to do a little bit of algebra. I'm going to move the natural log over to the other side. So I have p at some time t over p initial equals e to the kt. And we can finish out this by saying the population as a function of time is equal to the initial population, e to the kt. And so that is my population function at any value time. That's my general solution to my differential equation. That's my general solution to this differential equation. Now, what you'll see this in form of is y equals c, or y naught, e to the kx. It's the exact same equation, but that's in terms of y's and x's, the same exact function as well. So let's say we have what's the rate of change of y is proportional to y, and so I have this value right here, okay, which is p at some value t is equal to p naught e to the kt. I don't have to redo my general solution to my differential equation because I just did it, or you could call this y equals y naught e to the kx. It might be easier to take a look at it this way, my general solution. But now I've given you values, which means we know what my particular solution would be. We know that when t is equal to 0, when x is equal to 0, y is equal to 2, which means that is what y naught is. So we have y equals 2 e to the kx right here. And so we know our initial value is 2. Now they also told me when t is equal to 2, where x is equal to 2, y is equal to 4. So we have 4 is equal to 2e to the k times 2. So we're going to do a little bit of algebra here. We're going to divide by 2. 2 equals e to the 2k. We're going to natural log both sides. So natural log of 2 is equal to 2k, which means k is equal to natural log of 2 divided by 2. Natural log of 2 divided by 2. And so my natural log of 2 divided by 2 makes my k. Natural log of 2 is 0.693 divided by 2, which is the k is 0.34657. So I really know my particular solution now, don't I? My particular solution is y equals 2e to my constant is 0.34657 times any value of x. And now it says, what is the value of y when t or x is equal to 3? So now I'm going to plug 3 in for x right there, and you would end up getting y. You can try it on your calculator. Y equals 5.6568. And that means if you know these things, if you know an initial point, what a population is initially, you know what the population is at any value t. Using this function, you can predict what the population will be at any point in time. So you can take a look at the population of bacteria, population of people, population of pretty much anything. Okay. So let's take a look at an AP Calculus AB problem. This is a multiple choice problem. You can see it's problem number 84, which means we know we can use our calculator here. And it says population growth, dy over dt is equal to ky. This is a proportional growth. You can take a look, 1 over y dy equals k dt. We're going to do our separation of variables. We're going to do our integral right here. And we're going to go from y0 to y at some value t, time t to time 0. And so when we do our integral, what's the integral of 1 over y is natural log of y, and we're evaluating that from y0 to yt, and we have kt, and we're evaluating that from 0 to t, which means we have natural log of y at some value t minus natural log of y0 is equal to kt, going from t to 0, which means we have natural log of y at some value t over y0 is equal to kt. We do our little bit of algebra here, which means y at some value t over y0 equals e to the kt, which means y as a function of time is equal to the initial value e to the kt. And you're like, Aiden, we've already done that. Yes. Which means it's nice to know that equation. It shows up in Algebra 2, it shows up in Pre-Calculus, it shows up in every single course, and this is a proportionality. Now it says if the population doubles every 10 years, which means if the population was 1 initially, now the population is 2, e to the k, and that happened in 10 years. So you can use your calculator in order to do this. You're going to do your algebra, divide by 1. You do natural log of 2, which is 0.693, divide by 10, so k equals 0.0693. My AP chemistry students really know that k of 0.693 because that is a half-life. That's the great constant of a half-life. And I know my answer is 0.0693. So that was that nice kind of AP Calculus problem. Here is where we take this AP Calculus and AP Chemistry and we mix it together to find out what happens at Chernobyl. Okay, so if you can see, we have y equals y0 e to the kt. This equation happens for every half-life. It happens in chemistry, in every radioactive sample. And it says we know the half-life is 24,630 years of plutonium-239, which means if we have a sample of 1, it gets cut in half in 24,360 years, which means we can do my algebra to solve for k. We divide by 1. We do the natural log of 1/2. We divide by 24,360, and that is equal to k, which means k is equal to, if you do that on your calculator, is negative 2.845 times 10 to the negative 5. That is what my K is equal to. Now they want to know how long it'll take for 10 grams to decay to 1 gram. So we know our Y is going to be 1 gram. Our initial grams is going to be 10 grams. E to the K, what's my K, is negative 2.845 times 10 to the negative 5 times some value T. So I got to do a little bit of algebra. I'm going to divide by 10, so I get 1/10. I got to do the opposite of E, which is natural log of 1/10. Then I got to divide by negative 2.845 times 10 to the negative 5th. That equals your time T. And guess what? That ends up being, if I round up, it ends up being about 80,922 years, or about 81,000 years. Is that crazy? 10 grams to decay to 1 gram, it would take 81,000 years for the plutonium-239, the radioactive plutonium, to degrade to 1 gram. Just 1/10. That's it. 81,000 years. And that's why they still have a huge trash can lid over the city of Chernobyl, or the main reactor point in Chernobyl, and you can't even get near the plant site without governmental approval. Another really, really so cool thing is called Newton's Law of Cooling. Isaac Newton, Sir Isaac Fig Newton, ended up finding this out when he was away during a pandemic. So what are you going to do during your pandemic? I don't know. But Newton's Law of Cooling is so neat. What Newton's Law of Cooling says is that the rate of change of the temperature, so that means the change of the temperature with respect to time, and guys, I'm going to use capital T for the temperature, little t for the time. That's proportional to the difference between the object's temperature and the temperature of the surrounding medium. So it's, you can see my equation. I just developed my general differential equation here. My general differential equation is the rate of change of the temperature with respect to time is proportional, so K times some value proportional to the difference between the object's temperature and the temperature of the medium. Okay, so let's take a look at what they say. It says a detective finds a murder victim at 9 a.m. The temperature of the body is measured to be 90.3 degrees Fahrenheit. 1 hour later, the temperature of the body is 89.0 degrees Fahrenheit because the room is maintained at 68 degrees. We know the medium is at a constant 68.0 degrees Celsius, which means I have a differential. I'm going to separate my variables. So I get 1 over the object's temperature minus 68.0 change of the temperature equals K times change in the time, which means now I'm primed and ready to integrate, aren't I? Now, what are my limits of integration? I'm going to call my temperature initial temperature and temperature at some value T, or let's call it final temperature. And my time at some value T, T naught, T initial, and I'm going to call this T naught right here, if that's okay. And time at some final time. And so let's do our integration here. So we have natural log of the object's temperature minus 68 degrees Fahrenheit. And we're going from T initial, temperature initial, to temperature final. And that equals KT. And we're going from time initial to time final. Okay? So hopefully you're staying with me right now. And so let's start plugging some stuff in. Here we have natural log of my final temperature minus 68 degrees minus natural log of my object initial temperature minus 68 degrees equals KT final minus KT initial. KT final minus KT initial. Now let's take a look at our problem and see what they've given us. They've told me after 1 hour, the final temperature of the body is 89.0 degrees Fahrenheit. What's the initial temperature of the body at time 0 at 9 a.m. is 90.3 degrees Fahrenheit. And what is the final time is whatever time it is plus 1 hour. And what's the initial time? I'm going to call time t. Time t. So let's take a look at what I have. I have natural log of 89 minus 68. That's 22.3. No, it's not. 89 times minus 68 is 21. My bad. 21. 21. And then I have natural log of 90.3 minus 68 is natural log of 22.3. And that is equal to, if I distribute this, kt plus k minus kt. So, at the end of the day, you can see the kt minus kt cancels out, and this is going to help me solve for what k is. And k is equal to 21 degrees. So natural log of 21 minus natural log of 22.3. And that ends up giving me a k value of negative 0.06006. Okay, 42. So that's what my k value is. Now you're like, good night, this is hard. Well, it's not really all that hard. It's just a little bit of work. That's all it is. Now, I'm going to use the same general equation to find out what time this dude died at. So I have natural log of the final temperature. Well, I'm going to use for the final temperature this 90.3, if that's okay, minus 68. Minus natural log, because I know that's at time 9 a.m., is when he's 90.3. What was the initial temperature of the body? Well, bodies are usually at 98.6, isn't it? That's when they're living. Equals k times t final, that's t, minus k times t initial, time initial. And the time initial was time 0. So I want to know, I know the k is negative 0.0600642, and I want to know the time at which that dude died. And it tells me the time. The change in the time is 5.27 hours. This dude died 5.27 hours ago. So what time is that? Well, 9 a.m., take away 5, that's 4 a.m., take away 0.27 hours out of 60, and that would be 3:44 a.m. And we've figured out that this dude died at 3:44 a.m. Murder. Using Newton's law of cooling. Something found out a long time ago using calculus. Well, that is our last video. That's exponential models with differential EQs. And I am going to get exponentially better looking every single day, so you can use that model, because I am a model, to find how good looking I'm going to be tomorrow. See you guys. Bye.